Hi guys, I'm going to see if this works. I found a video on what the second derivative test tells you, and it's cool, so hopefully you can see and hear it.
Earlier, we saw how the sign, the SIGN of the derivative, encoded whether the function was increasing or decreasing. Thinking back to the graph, here I've just drawn some random graph. What is the derivative encoding? Well, here at this point A, the slope of this tangent line is negative, the derivative is negative, and yeah, the function's going down here. At this point B, the slope of this tangent line is positive, and the function's increasing through here. Right, the derivative's negative here, and it's positive here. The function's decreasing here and increasing here. So that's what the derivative is measuring. What is the sign of the second derivative really encoding? Maybe we don't have such a good word for it, so we'll just make up a new word. The SIGN, the sign of the second derivative, the sign of the derivative measures concavity. The word's concavity, and here's the two possibilities. Concave up, where the second derivative is positive, and concave down, where the second derivative is negative. And I've drawn sort of cartoony pictures of what the graphs look like in these two cases. Now note, it's not just increasing or decreasing, but this concavity is recording sort of the shape of the graph in some sense. Positive second derivative makes it look like this. Negative second derivative makes the graph look like this. And I'm just labeling these two things concave up and concave down. And this makes sense if we think of the second derivative as measuring the change in the derivative. So let's think back to this graph again. Here's this graph of some random function. Look at this part of the graph right here. That looks like the concave up shape from before where the second derivative is positive. So we might think that the second derivative is positive here. That would mean that the derivative is increasing. What that really means is that the slope of a tangent line through this region is increasing. And that's exactly what's happening. The slope is negative here, and as I move this tangent line over, the slope of that tangent line is increasing. The second derivative is positive here. You can tell yourself the same story for concave down. So look over here in our sample graph. That part of the graph looks like this concave down picture where the second derivative is negative. Now, if the second derivative is negative, that means the derivative is decreasing. And yeah, the slope of the tangent line through this region is going down, right? The slope starts off pretty positive over here, and as I move this tangent line over, the slope is 0 and now getting more and more negative. So in this part of the graph, the second derivative is negative. What happens in between? Where does the regime change take place? So over here, the second derivative is negative. Over here, the second derivative is positive. There's a point in between, maybe it's right here, and at that point, the second derivative is equal to 0. On one side, it's concave down, and on the other side, it's concave up. A point where the concavity actually changes is called an inflection point. Right? It's concave down over here and it's concave up over here, and the place where the change is taking place, we're just going to call those points inflection points. It's not that the terminology itself is so important, but we want the words to describe the qualitative phenomena that we're seeing in these graphs. Inflection points are something you can really feel. I mean, if you're driving in a car, you're braking, right? That means the second derivative is negative. You're slowing down. And then suddenly, you step on the gas. Now you're accelerating. Your second derivative is positive. What happened, right? Something big happened. You're changing regimes from concave down to concave up. And you want to denote that change somehow. We're going to call that change an inflection point.
Okay, that was a great introduction to our lesson on the second derivative test and what it shows you. So we're learning what the second derivative can tell you about the graph of a function and learning to use the second derivative test to find points of inflection and intervals over which a function is concave up or concave down. And then we're going to put the first and second derivative test together to sketch polynomial functions. So what does the second derivative test tell us about the graph of a function? Well, as we just saw through that video, it tells you where the graph is concave down, where it's concave up, and where points of inflection might be. So again, this just shows you here that here we have a concave down situation, and we can see that the slopes of the tangents are decreasing, so that the second derivative would be negative, and we have our concave down. And it also shows you what's happening with the first derivative. First derivative is positive, increasing, 0, and decreasing. So if dy by dx is 0 and the derivative is decreasing or negative, and the second derivative is negative, then we have a maximum. It also tells us that the curve is concave down, meaning the tangents would be drawn above the curve. Okay, so if you were to draw slopes of the tangents here, they'd be above the curve. And again, they're decreasing. So they're going from positive to 0 to negative. And in our second case here, we have the derivatives increasing. So we go from being negative to 0 to positive. So the second derivative is positive or greater than 0, then we have a minimum. And it also tells us the curve is concave up, meaning the tangents would be drawn below the curve. And if dy by dx is 0, and the second derivative, so this is a way of writing the second derivative another way. Ways to write the second derivative we saw in the video, f double prime at x is probably the most common way of writing the second derivative. We can also use y prime prime, which is common, but Leibniz notation, we say the second derivative of y with respect to x, you write it like that. So if both are 0, if the first derivative is 0 and the second derivative is 0 at a certain x value c, then the second derivative test should be done to determine if we have a point of inflection. And you'll see how we determine that. And you can see that this in this picture is a point of inflection because we change from being concave up to there, and then at our point of inflection, we become concave down. So that's what a point of inflection is, where you change from being concave up to concave down, or from being concave down to concave up. And then we've got that definition there. If the curve changes concavity at a certain point, then it's a point of inflection. All right, so consider the following function. F at x equals negative 4x cubed plus 18x squared plus 3. Use the first derivative test and the second derivative test to determine any local maximum and minimum values of the function. Okay, so first we're going to use the first derivative test. So I've got my f at x equals negative 4x cubed plus 18x squared plus 3. And I'm going to find the first derivative and put it in simplified factored form. So first derivative is negative 12x squared plus 36x plus 0. Now let's put it in factored form so we can common factor out negative 12x. Oops. Set it equal to 0. And solve for x, and those will be where our critical values are. So we can see our critical values would be when x is 0 and when x is 3. And now we can do the first derivative test. So we can use the short form, that's okay with me, f dt for first derivative test on f prime at x equals negative 12x times x minus 3. And then we use our critical values to make our intervals. So our first interval is going to be from negative infinity to 0. And then we want to know what our first derivative is at x equals 0. Our second interval is going to be from 0 to 3. Remember, we're splitting up the domain using 0 and 3. So this is our interval negative infinity to 0. This is our interval 0 to 3, and our interval 3 to infinity. We want to know what our derivative is at x equals 3, and then at 3 to infinity. And I like to put 3 columns in my chart. One is for the sign of f prime at x, then a little picture, and then a conclusion. So f prime at x, we want to know what its sign is between negative infinity and 0, so we can pick a representative value like negative 1. If we put negative 1 in for x, that would make negative 12x positive and negative x minus 3 negative. So overall, a positive times a negative is a negative. That would be a representative picture of a negative tangent. And our conclusion is that we'd be decreasing over that interval. If we sub 0 in, we're going to get 0, which is a horizontal tangent. From 0 to 3, a representative number would be like positive 1. So that's going to make this negative. Negative 12 times a positive would give me a negative. And then 1 minus 3 would still be negative. So a negative times a negative is a positive. So the sign would be positive, and we would be increasing, which makes this a minimum value at, or a minimum point at 0, and then f at 0, which is 3. Also is our y-intercept. Happens to be a minimum. At x equals 3, we get 0 again, 3 to infinity, so a number like 4. That's going to make this negative still, and this positive. 4 minus 3 is 1, so positive. So my, overall, f prime and x is going to be negative times a positive, which is negative, which means I'd be decreasing. So here we're going to have a local max at 3, and then f at 3. Which I can find on my calculator. So f at 3 is going to be negative 4 times 3 cubed, which is 27, plus 18 times 9 plus 3, 57. So there's our first derivative test. Okay? Now we'll move on to do our second derivative test. So I'm going to start off with my first derivative before I simplify. So f prime at x is negative 12x squared plus 36x, because this is the easiest form to find the second derivative in. So now we're going to find the derivative of the derivative, or the second derivative. So f double prime at x is negative 24x plus 36. And now let's put that in simplified factored form. So I can factor out negative 12, and that's going to give me 2x minus 3, set it equal to 0. And with the second derivative test, you're looking for where the second derivative is equal to 0, because that gives you possible points of inflection. So in this case, for this to equal 0, 2x minus 3 would have to equal 0, because negative 12 times 0 would be 0. So we would get x equal to 3 over 2, or 1.5. And now we're going to do the second derivative test. So the second derivative test, we can use s dt for second derivative test on our second derivative, f double prime at x equals negative 12 times 2x minus 3. And I forgot to do something here. Once we find our x equals 3 over 2, you want to do a little therefore statement for that as well, which I'll put over here. So therefore, a possible, we don't call them critical values, but a possible point of inflection is at x equals 3 over 2. And now we're going to see if it actually is a point of inflection, and that's where we use our second derivative test. Okay, so wherever the derivative is equal to 0, that's where you have a possible point of inflection, and then you do the second derivative test to see if it is. Okay, so again, second derivative test, similar to the first derivative test, only it's on the second derivative. So we've only got one possible point of inflection, so that's only going to be 2 intervals. So our first interval is going to be from negative infinity to 3 over 2. Then what happens when x equals 3 over 2? And then our second interval is 3 over 2 to infinity. So again, we'll have our f double prime at x. We want the sign of f double prime at x. We want a representative picture and a conclusion. So between negative infinity and 3 over 2, I could choose 0 fits in there. That's going to make negative 12 is always going to be negative. This is also going to be negative, and this negative times negative is a positive. So my picture now is a positive second derivative means concave up. So our conclusion is I'd be concave up over this interval, which is really helpful when you're sketching your picture. When x equals 3 over 2, we get 0. 3 over 2 to infinity, so a number like 2, for instance, this is going to be negative, this is going to become positive, and a negative times a positive is a negative, which means we're going to be concave down. And because we're changing from concave up to concave down when x is 3 over 2, there's going to be a point of inflection. You just draw a little point in there. So point of inflection at 3 over 2, but then I have to find f at 3 over 2. Okay, which can take work. I'm going to get a scrap piece of paper to do that here, if you have one handy. So f at 3 over 2, you can get it on your calculator. You can also get it writing it out, but f at 3 over 2 is going to be negative 4 times 3 over 2 cubed. I'll do it out the long way. And then I'll do it on my calculator and we can compare. So f at 3 over 2 is going to be negative 4 times, so 3 cubed is 27 over 8, plus 18 times 9 over 4, plus 3. So I can see that if I multiply by 4 by 27 and reduce, 4 is going to go into both top and bottom, so I'm going to end up getting negative 27 over 2 here, plus the 4 and 18 divide out, so that's going to give me 9 over 2, so 81 over 2, plus if I want a common denominator of 2, that's going to be 6 over 2, which is going to give me negative 27 plus 81 plus 6, 50 over 2, which is 25. Oops, 50 over 2. which is 25. Sorry. And then let's try just subbing it into our calculator. So -4 times 3/2 to the power of 3 plus 18 times 9/4 plus 3, 30. Did I do something wrong here? 27/8. 18 divided by 2, 4 divided by 2. Oh, 9 times, no, that's right. 6. Oh, this is 60, my bad. 60/2 is 30. So it works out the same on the calculator and doing it out. So this is at, sorry, our point of inflection is at 3/2 and 30. Okay, so using that, all that information we've got from our first derivative test and our second derivative test, we're going to do a sketch. So I'm going to draw, so I can see that I have a point of inflection at 1.5 and 30, a max at 3 and 57. So everything's going to be pretty much above the x-axis. So I'm going to make my x-axis lower down here. And my y-axis. So there's my x and y-axis. And remember, this is just a representative sketch. We do the best we can, but it doesn't have to be on graph paper. We just have to label all our important points. So I see that I have a minimum at 0 and 3. So I'm going to put a point on here and label it 0 and 3. And then I've got a point at 1.5 and 30. So I'll make this 2, so this is 1. So 1.5 and 30, I'll just make a representative point here. Sorry, yeah, 1.5 and 30. So we'll call that 3/2 and 30. And then we've got this point at 3 and 57 as well. So 3 and 57. And we can see that 0,3 is a minimum. And we can also see that we're concave up between -infinity and 3/2. So between here and here, we're concave up. So that gives us really good guidance to draw this in. Concave up, concave up. And sure enough, that's a minimum. And then from our second derivative test, from 3/2 to infinity, we're always concave down. So concave down, up to a maximum, and then always concave down. So there's a sketch. And then you want to use your test to make sure that your sketch makes sense. So if I look at my first derivative test here, I should be decreasing from -infinity to 0. So from -infinity to 0, I am decreasing. And then I have a min at 0,3. I should be increasing from 0 to 3. So from 0 to 3, I am increasing. I should have a max at 3 and 57, which I do. And then I should be decreasing from 3 to infinity, which I am. And then also the second derivative test tells you where you're concave up and concave down and where you have a point of inflection. So we've labeled our minimum, our point of inflection, and our maximum. Our increasing and decreasing, our first derivative test agrees, and our second derivative test agrees. So that is Correct. So that's using the first and second derivative test to make a sketch. Okay, so definition, a point of inflection is a point at which a curve changes concavity. So in this case, here's our point of inflection. Since concave up corresponds to a positive second derivative and concave down corresponds to a negative second derivative, then a point of inflection only can occur at places where the second derivative is 0. Okay. The second derivative test, if f double prime at a certain value c is 0 or undefined, if we had more time, we would do rational functions. So you would see where the denominator is 0. Those are where possible points of inflection occur. If it is a point of inflection, then f double prime at c changes from either positive to negative or negative to positive at that value. So on intervals where the second derivative is greater than 0, we're concave up, the tangents would be drawn under the curve. And on intervals where the second derivative is negative, the curve is concave down. Okay, so determine any local maximum or minimum values and any points of inflection for each of the following functions. Make a sketch of the function, i.e. apply both the first and second derivative tests. Okay, so step 1, let's find the first derivative. And then we want to put it in simplified factored form. So I can factor out 4x. And also I can factor x squared minus 1 as a difference of squares. Set it equal to 0 to find my critical values. And then I can see that x equals 0, x equals -1, and x equals +1 are my critical values. Critical values at x equals 0, +, -1. So now I can do my first derivative test. So my intervals are going to be from, so I'm using 0, -1, and +1, so from -∞ to -1, from -1 to 0, from 0 to 1, and from 1 to infinity. You may want to know the sign of the first derivative, a little representative picture, and a conclusion. So I'm going to choose -2, fits in the interval -∞ to -1. That would make 4x negative, would make x + 1 negative, and x - 1 -1. So 3 negatives make a negative. I'd be decreasing. 0 at x equals -1. So a number like -1/2 would fit between -1 and 0. Still makes this negative, but -1/2 + 1 is positive, and this would still be negative. So that's going to give me an overall positive. 2 negatives make a positive times a positive, so I'd be increasing, which makes this a local min at -1, and then we go here. So we want to know what's y when x is -1. Oops, can't see that side of the camera. So -1 to the 4th minus 2 times -1 squared plus 7. positive 1 minus 2 plus 7 is 6. So we have a min at negative 1 and 6. At x equals 0, again, our first derivative would be 0, horizontal tangent. From 0 to 1, so that's a number like a half, that's going to be positive, positive, negative, so we're going to be decreasing. So here we would have a local max at 0. And then if you sub 0 into the original, you can see you're going to get 0 minus 0 plus 7. So you can kind of just do that one in your head. X equals 1. 1 to infinity is a number like 2. Positive, positive, all positive. So we'd be increasing, which means this would be a local min again, this time at 1. So if we sub 1 in, we're going to get the same again because we're putting them to an even power. So 1 minus 2 plus 7 is again 6. So there's our first derivative test done. Now we're going to do our second derivative test. So first of all, we're going to take down our first derivative before we put it in factored form, so 4x cubed minus 4x. Take the second derivative, the derivative of the derivative. So that's 12x squared minus 4. And can we factor that? We can factor out 4. But that's not a nice difference of squares. Still want to set it equal to 0. And solve for x, which just isn't going to be quite as easy. So for this to be 0, 3x squared minus 1 would have to be 0. Which means 3x squared would have to be 1. X squared would be 1/3. So we get, if we square root both sides, x is positive or negative 1 over root 3. So therefore, possible points of inflection occur at x equals positive or negative 1 over square root of 3. So now we can do our second derivative test. So s dt on y double prime equals 4 times 3x squared minus 1. And our intervals are going to be based on our possible points of inflection, so negative infinity to negative 1 over root 3. X equals negative 1 over root 3, negative 1 over root 3 to positive 1 over root 3. And then our last interval is going to be from positive 1 over root 3 to infinity. And we want to know the sign of y double prime, a representative picture, and a conclusion. So from negative infinity to negative 1 over root 3, so that might be a number like negative 2. So this is always positive, so it's not gonna, it's fine. Here, if we square negative 2, we're going to get positive 4. Times 3 is 12, minus 1 is going to be a positive. So we're positive here, which means we're concave up. We're 0 here. 0 is in this interval, so that makes it easy. This one's going to be negative now, because 3 times 0 is 0 minus 1 is a negative, so we're concave down, which means we do have a point of inflection at, okay, so this is a little bit trickier here, so it's at -1 over root 3 and something. So again, I'm going to get a piece of paper we can look at here, substituting into the original. So y equals -1 over root 3 to the power of 4 minus 2 times -1 over root 3 squared plus 7. So -1 to the power of 4 is +1. Root 3 to the power of 4, we'll think about that in a second. Minus 2 times -1 to the power of 2 is +1. And root 3 squared is 3. We do know that, plus 7. So here we know that root 3 squared is 3, and then we would square again and get 9. Minus 2/3 plus 7. We want to get a common denominator here of 9. 2 times 3 is 6. And we would end up getting y equal to let's see, 1 minus 6 plus 63, 58 over 9, which doesn't reduce. So there we go. And if you want to double check on your calculator, so you can have -1 over the square root of 3 to the power of 4. Oops, I didn't type that in right. So -1 divided by the square root of 3 to the power of 4. Minus 2 times -1 over the square root of 3 squared plus 7. So that's the decimal we would get, and 58 over 9, also the same. Okay, so we know we're right. So we know that we have our point of inflection at -1 over root 3 and 58 over 9. 0 here, a number like 2 is going to make this positive, so we're going to be concave up. And we're going to have another point of inflection at +1 over root 3. Now you can see what would happen if I just changed this to +1 over root 3 in all of these cases. I'm still going to get a +1 here and a +1 here. Nothing else is going to change, so I'm still going to get 58 over 9, which is nice for us. Okay, so we've done the first and second derivative test. I'm going to squeeze in a small sketch here. So I see that these are above 0 and up here above 0. So I'm going to make my little sketch here. Remember, it's just a sketch. As long as we can label all our points. All right, so -1 and 6, I've got a minimum. And remember, 58.9 was 6.444, so a little bit above that. So -1 and 6, I'll put here. So -1 and 6. 0 and 7. 0 and 7. Got a max. Another min at 1 and 6. So that's going to be like the same distance on this side. 1 and 6. And then -1 over root 3 is -0.6 about. And we know, so -0.6 and about 6.44 is going to be about here. So that's going to be our negative, so we'll label that point down here, -1 over root 3 and 58 over 9. And then there's going to be one the same distance away here. And that's going to be +1 over root 3 and 58 over 9. And we know that we're concave down between -1 over root 3 and +1 over root 3, so concave down. And then we're always concave up from -infinity to -1 over root 3, so here we go, concave up. And here, always concave up. And then we want to follow our first derivative test. So are we decreasing from -infinity to -1? Yes. Minimum at -1, 6, yes. Increasing from -1 to 0, yes. Maximum at 0, 7, yes. Decreasing from 0 to 1, yes. Minimum at 1, 6. Increasing after that, good. And then concave up from -infinity to -1 over root 3. Concave down from -1 over root 3 to +1 over root 3. Concave up from 1 over root 3 to infinity. So there's a good representative sketch with all our important points labeled, all of our max, mins, and points of inflection. Okay, so that's how you use the first derivative test and the second derivative test together to give you a good sketch of a polynomial function. Okay, here's another one to try. So y equals x cubed minus 3x plus 5. So we'll start off finding y prime. So that's going to be 3x squared minus 3. Put it into simplified factored form. So we've got a difference of squares here. Set equal to 0. Solve for x. So therefore critical values at x equals positive and -1. So now we'll do the first derivative test on y prime equals 3 times x plus 1 times x minus 1. Our intervals will be from -infinity to -1, -1 to +1, and 1 to infinity. And we want to know the sign of y prime, a picture, and a conclusion. So from -infinity to -1, I could pick a number like -2, which would make this negative and this. So overall I'd be positive, which means I'm increasing. My tangents would be positive. X equals -1, tangent 0. Between -1 and 1, I could choose 0, which would make this positive and this still negative. So overall I'd be negative or decreasing, which means I should have a max or local max at -1, and I can come up here and sub in. So it's going to give me -1 plus 3 plus 5, 7. And then at x equals 1, 0, number like 2 fits in this interval, which makes both of these positive, so I'd be increasing. And here I would have a local min at 1 and in this case, it would be 1, 3. All right, so there's my first derivative test. Now I'm going to find my second derivative, so I'm going to start with my first derivative in unsimplified form. Take the second derivative, set it equal to 0, and we get that x is 0. So possible point of inflection at x equals 0. And then we're going to do our second derivative test on y double prime equals 6x. So we only have one possible point of inflection at 0, so our interval is going to be from -infinity to 0. And from 0 to infinity. And we want to know the sign of the second derivative. Put in a little picture, and then say our conclusion. So a number like -1 makes this negative, so I'd be concave down. 0, I'm 0. 0 to infinity is a number like 1, so I'd be positive or concave up. So I do have a point of inflection. At 0, which is easy to sub in to the original, 0, 5. And now I'm ready to draw my picture. So move this up. Hopefully we can fit both tests in here. So I have 0, 5, -1, 7, so most things are above the x-axis here. So I've got my x-axis and my y-axis. So I have the point -1 and 7. So make this -1 and 7. 0 and 5. 0 and 5. And 1 and 3. And I know that I'm concave down from -infinity to 0, so I'm concave down here. And I'm concave up from 0 to infinity, concave up here. Check my first derivative test. Am I increasing from -infinity to -1? Yep. Max at -1, 7? Yep. Decreasing from -1 to 1? Yep. Min at 1, 3? Yep. And then increasing after that. Got my concavity. My important points labeled, done. Okay, our last example, y equals 3x to the 4th minus 8x cubed plus 7. This is a good example because a little something different happens here. So first let's find our first derivative. Y prime is going to be 12x cubed minus 24x squared. Simplified factored form, so 12x x squared, factors out, common factors out, and I get x minus 2 set equal to 0. And I can see that this is true if x is 0. For x squared to be 0, x would have to be 0. And for x minus 2 to be 0, x would have to be 2. So therefore, critical values at x equals 0 and 2. So we're going to do the first derivative test on y prime equals 12x squared times x minus 2. And our intervals are going to be from negative infinity to 0, from 0 to 2, and from 2 to infinity. And we want to know the sign of y prime. We want to know, draw a little pick, and then have a conclusion. So from negative infinity to 0, so a number like negative 1, well, x squared is always going to be positive. This would be negative if we choose a number like negative 1 to represent this interval. So we have negative decreasing. 0 to 2, that's a number like 1. This is still going to be negative. So I'm decreasing still, which means not a max or a min. Not max or min here, which we haven't come across before. So this is a good example for that. X equals 2 or 0. 2 to infinity is a number like 3, which makes this positive. So we're increasing here, which means that we would have a local min at 2, and then we have to come and sub in here. So that's going to be 8 times 16, sorry, 3 times 16 minus 8 times 8 plus 7, negative 9. So we have a minimum at 2 and negative 9. All right, so now we're going to start with our second derivative. So first let's take our first derivative in unsimplified form. And now take our second derivative, or the derivative of the derivative. And that's going to give me 36x squared minus 48x. So I can common factor out 12x from here and get 3x minus 4 set equal to 0. And this would be true then if x is 0 or 3x minus 4 is 0, which means x would be 4/3. So therefore, possible points of inflection at x equals 0 or 4/3. So now we're going to do the second derivative test on y double prime equals 12x times 3x minus 4. And our first interval is going to be from negative infinity to 0, then from 0 to 4/3, and from 4/3 to infinity. And we want to know the sign of y double prime, a picture, and a conclusion. So if we pick a number like in this interval, like -1, it's going to make this negative, and also this negative, so overall we'd be positive or concave up. 0. 0 to 4/3 of 1 works. So this is going to be positive and that's going to be negative, so we'll be concave down. Which means this is a point of inflection. at 0, and subbing in 0 is easy here, 0, 7. Notice that a 0 is also a critical value where we had not a max or min happening. And at 0, it turned out it was a point of inflection. It wasn't a max or a min, it was a point of inflection. So if you have neither max or min in your first derivative test, chances are it will turn out to be a point of inflection when you do your second derivative test. X equals 4/3 would make this 0. So this is a number like 2, which would make this positive as well. So we're concave up again. So we have another point of inflection. This one at 4/3. And then we have to figure out what happens when we sub 4/3 in here. So let's come up here. So 3 times 4/3 to the 4th minus 8 times 4/3 cubed plus 7. So that's going to be 3 times 4 to the 4th is 256 over 81 minus 8 times 64 over 27 plus 7. I know 3 goes into 81 27 times. So it looks like my common denominator can be 27. 8 times 64 is 512. And if I make 7 with a common denominator of 27, 7 times 27 is 189. So I end up getting 256 minus 512 plus 189, negative 67 over 27, which doesn't reduce, it's about negative 22.3 repeat, or negative 22 1/3 if you want to remember that for when you're doing your sketch, like where to put it in relation to other things. But that's going to be where our other point of inflection is. So 4/3 and negative 67 over 27. Remember, that's approximately negative 22 1/3. Oops, sorry guys, I didn't see that there. I finished the point of inflection coordinates. Okay, so we've done our first and second derivative test. All we have left to do is make our sketch. And let's look where we've got a negative, and a positive point. But we need more room below the x-axis. So we've got the point 0.7 I'll put here. We've got the point 2, negative 9, which I'll put here. Sorry, negative 67 over 27 is not negative 22 1/3. Negative 67 over 27 is actually negative 2. That wasn't going to make sense. I could see when I was drawing it. So negative 2.48 approximately. So here's say 1, here's say 2, so 2 and negative 9. And now 4/3 is 1 1/3 and negative 2.5. So 1 1/3, negative 2.5 stays about here. So we'll label that 4/3 and negative 67 over 27. And we're concave up from negative infinity to 0. So concave up from negative infinity to 0. Concave down from 0 to 4/3.